Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we'll start chapter 12 on Euler-Maclaurin summation. We'll start by giving a continuous version of Brion's theorem. The theme of this chapter are continuous versions of a lot of the things that we've done so far. And so we'll start with integer point transforms. It turns out when we convert sums into integrals, it's most convenient to have exponential variables. So we'll start with our discrete integer point transform, usually called sigma sub p, for some polyhedron p, and an exponential variable. So what this means is simply, if I have d variables, this is the variable e to the z1, e to the z2, and so on. And so our integer point transform becomes a sum over exponential functions of the dot product of an integer point with this variable z. And so the continuous analog of this is the integral. So now we integrate over the exponential function of the dot product x dot z, and the integral is a multivariate integral in x. The connection from left to right is essentially given by the Riemann definition of an integral. So we can go from the discrete integer point transform to the continuous version by refining the lattice. Instead of summing over all integer points in P, I'm summing over all fractional points with denominator n, and then together with the correct normalizing factor, I let then n go to infinity, and this gives me the integral. This will be the theme of today's video. We will show how to go from Brion's theorem that we discussed in the previous chapter to sort of an integral version of it. And one step in the proof of this continuous version of Brion's theorem will be precisely this limit. But in the next video, we will actually show how, in some sense, to go from the integral to the discrete integer point transform. And this is in some sense the real theme of chapter 12. And this connection usually goes by the name of Euler-Maclaurin summation. Anyway, we'll leave this direction to the videos to come and concentrate for now on Brion's theorem. Let me remind you of the previous chapter. So the main theorem here was theorem 11.7. We have a rational polytope, and Brion's theorem says that we can write the integer point transform of this polytope as a sum over rational functions representing the integer point transforms of the vertex cones. The continuous analog of this theorem is theorem 12.3. So again, we have a rational polytope, but now we have to assume it's simple. Let me remind you that this means that at each vertex, I see exactly d edges if my polytope is d-dimensional. You will see why we need this condition. At any rate, so now the philosophy of this theorem is precisely as in the discrete version of Brion's theorem. On the left-hand side, we have the integral of an exponential function over the polytope p. And on the right-hand side, we have a sum over all vertices of rational functions. And we will see that these rational functions naturally come from integrating over the vertex cone. To write this down, we need to fix a set of generators for each vertex cone. each vertex cone is a simplicial cone because my polytope is simple. So I have D generators. And so on the right-hand side, you see two kinds of ingredients. There's sort of an exponential that depends on the vertex. And there's a factor over here involving the determinant that depends on the generators. I want to make a quick remark and remind you of our chapter on zonotopes, where you've seen determinants before. This is when we considered tilings of a zonotope into parallel pipettes. And back then, we pointed out that there is a connection between the discrete and the continuous volume of a parallelepiped. And of course, the continuous volume is given by determinants. And it's this philosophy that will give rise to the determinants in Theorem 12.3. Let me give you an idea how this continuous version follows from the discrete version of Brion's theorem. Let's recall the setup. So if I have a vertex, we will write the vertex cone. Let me use the same shorthand notation from the previous video as I have an apex V. And my cones are simplicial, so I have D generators, and we call them W1 of V through WD of V, and I need this notation because we will have to deal with all vertex cones at the same time. Okay, so let's recall how we computed integer point transforms of simplicial cones. We first computed this fundamental parallelepiped. If I use the same shorthand notation, I can write this as a Minkowski sum of V and then the generators, where now my coefficients are between 0 and 1. And 1 is not included. And then my integer point transform of this vertex cone, let me first write it in the variable z, and then we can go to the exponential version in a moment, will be the integer point transform of this parallelepiped divided by a product of 1 minus z to the generators. Now I'm going to take this apart a little bit and give this parallelepiped just spanned by the generators a name. Let's call this pi sub v. And let me, for the time being, assume that I have an integer polytope. That means the generating function up here can be written as z to the v times the integer point transform of this sort of slightly new parallelepiped pi sub v. And now I'll go to exponential variables and use the original Brion theorem. So we'll compute the integer point transform of the polytope. Brion says that we have a sum over vertex cones, and we'll need to sum the integer point transforms of the vertex cones. If I write them in an exponential variable, what I will see here is my z to the v becomes an exponential variable in the dot product v dot z. Then I have the integer point transform of this parallel pipette pi v. And my product in the denominator, let me write it as a product over j from 1 to d. I now have, well, again, exponential variables. So I have 1 minus an exponential variable w j dot z. Now, to get integrals out of this, we know that we'll have to replace this sum over here. So after all, this is an exponential sum. We'll have to sum this over all integer points in P. But now what we'll do is we'll rescale the integer lattice by a factor of n. And now if we take this as n goes to infinity and normalize appropriately, that will get you exactly the integral. So now let's see what happens on the right-hand side. What we'll need to do is we'll scale every integer point down by n. Well, the apex of my vertex cone is still v, but now the integer point transform of my parallel pipette pi v, I can sort of think of just keep summing over integer points, but scaling them down by a factor of n. And the same thing happens with the generators, of course. And so again, in my product down here, I scale each generator by a factor of 1 over n. And at this point, you can see I did not really have to assume that my polytope was an integer polytope. My vertices can be rational vertices, and in this case, I might only go through integer multiples n that give me the right fractions. But at any rate, let's see what happens. If you now let n go to infinity, and I need sort of the normalizing factor 1 over n to the d in front of everything, on the left I get the integral. And on the right, well, there's n in here, and I claim what you're doing here is you're computing the volume of these parallel pipettes. So here this is really first principles of a Riemann integral. This will be the volume of pi v. And we've seen this volume can be expressed as a determinant, and this is precisely what appears in the continuous version of Brion's theorem. And now what we'll do in the denominator, we're going to move this 1 over n to the d into this product, and we'll have an extra factor of n everywhere. And this expression over here, this is really just a simple application of L'Hopital's rule. As n goes to infinity, you can convince yourself that this approaches the quantity negative wj dot z. And this gives you theorem 12.3.